Hi everyone, my name is Jan Brugård and I'm the CEO of Wolfram MathCore, the Wolfram subsidiary responsible for the development of Wolfram SystemModeler. Today I'm going to give you a quick overview of the new features in SystemModeler. But as some of you might be new to SystemModeler, I will begin with a quick introduction to the software. As the name indicates, it's a software for systems modeling. So the question is, what kind of systems are we talking about? As a matter of fact, it can be many different types of systems, with a common denominator that we are interested in understanding their dynamic behavior. Whether we would like to model an aircraft to develop and test its control system, an excavator to optimize the hydraulic system, or a metabolic pathway to study diabetes therapies, SystemModeler has the component libraries and tools for this. Talking about having the components needed to model all sorts of systems, have you ever wondered if it's possible to build a jetpack using downward firing machine guns? Well, that's the question asked in Randall Munro's What If article, Machine Gun Jetpack. Let's study the real physics of this improbable flight to exemplify the use of SystemModeler. I will start SystemModeler from Mathematica. First, I load SystemModeler with needs WSM link, where WSM stands for Wolfram SystemModeler, of course. Then I open the model of a squirrel before I start the model center, where we see the model diagram for this for our first model. We'll start with a squirrel with one machine gun. And the model has 4 different components: the squirrel itself, the gun, a position sensor, and the crash detector. Each of these contain the equations needed to describe each subsystem. If I double-click on the squirrel and go into its component mode, we can see that the squirrel is simply described as a mass with a gravitational force acting on it. It's a highly simplified version of a squirrel, of course, but it's enough to get the fidelity needed for our purpose. If we want to make a more detailed model later on, we can do that. The gun model, on the other hand, is slightly more advanced, consisting of a magazine where you have the bullets and the release logic for them, the gun itself, and the bullet that we're currently shooting. Let's simulate and then plot the position of the squirrel. I do that by selecting the position sensor and plotting. We can see now that if we're using one gun with one bullet, the squirrel would reach a maximum height of about 9 centimeters or 3.5 inches. I'm pretty sure that the squirrel could jump higher than that if it wasn't using the machine gun. But that said, we have proven the concept. So let us return to Mathematica and see if we can use SystemModeler from there to investigate the flight of a human being instead. I set up the parameters from AK-47 and let a human use 1 or more machine guns to propel himself. If we look at the simulate command, we can see that we are simulating a model for the human being now, and that we have a list of parameters to choose the number of guns, and also a parameter to set the number of bullets. So we simulate this and look at the results. What we see is that height will depend, of course, on number of guns, but also we can see that as a function of time, they will vary. So if we look, for instance, at the first one with only one gun, we will hardly notice anything. Of course, we will not get any height at all. But if we look at the other ones, like the last one, we can see that we get a substantial height. But perhaps most interesting is the version with 32 guns. In this, we can see that we start increasing in height first, just as expected, before for some reason we start to lose height, and then we increase again. Then we run out of bullets, of course, and we crash. So how come we have this dip in the middle of our flight? Well, that's the kind of questions that you can answer and get, of course, by doing simulations. So whether this is, as in this case, a human being trying to propel himself with a machine gun jetpack, or a biochemical pathway to study diabetes, an excavator to study the hydraulic system, or an aircraft to design the control system, you can use SystemModeler for those purposes. Okay, so after this really quick introduction to SystemModeler, it's time to see what we've done during the last year. And I'll begin with version 4.1. So 4.1 focused on three main areas: FMI, reliability, and model development. If we start by looking at the first one, FMI, it's a way to import models into SystemModeler from other tools. I will exemplify this with this example, which we will not run live, but will give you the idea of what you do. So basically, in this case, we have designed a control system in Simulink, or somebody has done that. And then we want to use this control system to test it in a with a realistic model. So to do that, we want to use SystemModeler, as that's a very good tool for developing the model of the driveline. So using FMI, we can export the control system from Simulink, then import the very same system into SystemModeler, and then run them together. This means that we can now do all the same simulations as we typically do in SystemModeler, and analysis as well as design tasks within Mathematica. So this gives us a very powerful tool in order to integrate in tool chains that include other software. Now, let us take a look at what we added for reliability. To exemplify this feature, I will use the following model of the flap systems of a Cessna Conquest 441. I open the model in SystemModeler, and we can see what the model consists of. It has the pilot, electric circuit, the flaps, the hydraulic power system, the landing gear, and so on. What we can see here is that we have a reliability tab under the diagram. So let's click on that. What you can do in 4.1 is to define reliability distributions like this. You can choose from all the reliability distributions from within Mathematica, and then select the reliability distribution and how it depends on the different components of your system. In this case, we only included the flaps and the hydraulic power system. But then we can dig into the hydraulic power system, and here we can see that likewise the hydraulic power system has its reliability distribution, where it depends on the different pipes and possibly other things that we don't see in the view right now. So this way, if we go into the pipes, we will see other distributions, and step by step we'll build up the complete reliability of our system. So if I return to Mathematica, we can now look at the different fault modes of a pipe. So each pipe has been modeled with 3 different fault modes. The pipe could either be leaking, or you could have restricted flow, or even blocked flow. So depending on this, of course, we will have different, might have different system failures, different consequences. But what we can do now, as we have modeled the reliabilities of the system, we can simulate simulate the reliability of the system, including its subsystems, and compare the results. So here we can see that, of course, the complete system has a lower reliability than each subsystem, which we would expect, of course. But we can also see the relationship between the flap system and the hydraulic power system, where the flap system seems more reliable than the hydraulic power system. So that tells us that perhaps it's in the flaps in the hydraulic power system that we should look into improving. There are many other things you might want to dig into, of course. For instance, the Wolfram language includes 9 different importance measure functions, starting from the very basic structural importance and going to more advanced measures. Let's find out which failure in the basic pipe would be the best to improve. Clearly, the cases where we have restricted or even blocked flow seem to be of larger importance for the system's reliability. Of course, different failures will cause different types of problems, and this is something you can use the system simulation for. But together, this gives you a very good tool to analyze and improve your system. Okay, so let's jump ahead from 4.1 to the new model libraries that we have developed during the year. One of those is Model Plug. Then we have OPC Classic and the hydraulic library. So if we begin with Model Plug, we can click on that, and I'll go to the web page, or rather to a blog describing it. So Model Plug, what it does, it's for those of you that haven't used it before, it makes it possible to easily connect SystemModeler models with Arduinos. So basically, with drag and drop, you can configure your connection to an Arduino, like here where you see the Arduino board, and then you can see here, like connecting a dimming LED with a connection where the simple model is a sinusoidal signal from SystemModeler. Here we have a robot controlled from SystemModeler, and we can connect different things. Like in this case, we have created a model of an inverted pendulum in SystemModeler, and then used an accelerometer connecting through an Arduino to control it. So we can just play it and see here how it works. Okay, so that's what Model Plug is all about. And what we've done is that we released version 1.1 beginning of during last year, and then beginning of this year we have released the version 1.2, so it's really new. And what we can see, what it has added, 1.2 is connectivity with new boards such as Mega, and 4.1 actually with Leonardo, and then we have improved support for Windows 10. If we skip ahead to the OPC Classic library, it is similar in a sense, but deals with systems connected through the OPC Classic protocol, a standard that is used a lot, especially within process industry. The OPC library contains a full set of components for connecting to physical systems using this standard. So if here we also, when launching the OPC Classic library, we wrote a blog, and it's a very good blog for you to see what it's all about. It shows how you can connect, use OPC to connect for instance, with different processes, as you can see illustrated here. If we take a look at the model diagram below, we can see that we have a metabolic pathway for a bioethanol process in this case, and the model is used in the center, and then we have a bunch of connections to different OPC servers. And then this model is used for model predictive control of the bioethanol process. So of course the ambition with this is to optimize the production of bioethanol. So let's return and go ahead to the hydraulic library. I will not talk too much about it, as we looked a little bit into it in the Cessna Conquest example. But a new version was released, version 1.1, or will soon be released. And what you can see in that version is that we added, for instance, hydraulic filters. So now you can include those in your models. And we've also done a redesign of the parameters, or set better parameter values, so it's easier to use the components right away. And of course done some bug fixing to improve the library. But we'll go ahead and look at 4.2 instead. So just as 4.1, 4.2 we focused on 3 different features, in this case performance, usability, and Wolfram language integration. And I will exemplify these 3 with 3 different small examples, just pinpointing a little bit of what we've done. Performance improvements is something that you will enjoy when you're using the product. Everybody will do that. And in fact, there are 2 main areas in which performance has been improved: model compilation and plotting within SystemModeler results from within Mathematica. Let's start looking at the latter first. If we look at this graph, it illustrates the time needed to plot in version 4.2 compared to 4.1 for a set of test examples. We can see that for all these, time has gone down, and in most cases it's gone down substantially. In fact, if we look at the average, is probably just takes about 0.2 to 0.4, 20 to 40% of the time that it used to take, even though some still take just about the same time as before. In general, you can say that results with a lot of dynamics have improved their performance most. And that's, of course, of big interest for us, because we are looking into dynamic systems and we want fast plots when plotting system dynamics. We can see that what we've done is actually to improve build performance of these large models. So the time it takes for you you have developed your model until you can simulate it has been improved substantially. So what we see here is 4.2, 4.1, and 4.0. Besides other end types, it takes for a set of test examples from a scalability test suite developed at the University of Milano. So what we can see here is that 4.2, if we look at all of the examples, is substantially faster than its predecessors. And if we look at the 6th example here, we can see an even bigger difference, because in 4.1 and 4.0, those examples did not even build. Now they take a relatively small amount of time to build. So this, as I said, will be a huge improvement for all of you working with large models. So next area we focused on was integration with Mathematica and the Wolfram language. And one such example is WChain create model, which we added. This makes it possible to define models in data models in Mathematica and create system modeler models with a simple command. So in this case, we create a noisy data model using Mathematica. We can then connect these either in the model center, as we looked at for the Cessna, for instance, or as we did here, programmatic for the Mathematica, and then simulate and look at the results. I have the results since before, and now, of course, if I repeat the plot, I should expect to have another result, as we are dealing with random numbers. So last but not least, for 4.2, just as for 4.1, we added a bunch of small things to improve usability. And in this case, I will illustrate one for Model Center and one for Simulation Center. So let's look at this small model of a robot where we have an input defined by a table, and then we have this controlling the robot arm. If I select the robot and go to the Parameters tab, I can see here, of course, there's a bunch of parameters like the table defining the positions or the inputs that will give the positions for our robot. So to edit this, you did this in this field before, and you can still do that. But that was really cumbersome. What you tended to do is to copy this and paste it to some other notepad in order to see more than you see in this small view. And that was, of course, not desirable. So what we done, we added a specific editor for this, where you have where you can get a much better view of your matrix, and you can edit here, change your values, and copy and paste, and so on. Of course, this makes it the process of setting the right numbers facilitates that quite a lot. But likewise, we've done similar things for other things. So this is one of the editors, but similarly, if you were about to set, let's say, a path for a file, you needed to type that in. Now you can use your built-in Finder or browser to do that. And we added for color picker, if you rather than setting the RGB code, writing that, you use a color picker and so on. And this is just one example of things we've added in the Model Center to make it easier to model. So let's look at Simulation Center instead to give an example from there. So we'll simulate this example and look at the animation. It's not that spectacular of example, but let's see what it does. So, well, it's kind of moving up and down and doing something. It's perhaps it's a little bit hard to see what it did. So what you can do now from 4.2 is that you can select different parts of your system, like here, and you can see there's trace path, and you can do that for the different parts. Like here, I go look here, trace path. But I'll select, in this case, I want to trace the path of the tip of my robot arm, so I'll select that. And once selected, I will run the animation again. And now it should be much easier to see what this is all about. So Wolfram SystemModeler, a lot of improvements during the last year, 4.1, 4.2, and libraries added upon that. So with that, it's time to wrap up this presentation, and I'll do that by giving you a little bit, quick overview of the upcoming presentations in this virtual conference. So first we'll have a deployment of standalone Mathematica models to the Raspberry Pi and Arduino, and that will be presented by Leonardo Laguna. And then we will continue with how to model 10 helicopters in a single model. So this deals about configurable models basically, and the presenter in this case will be Marcus Dahl. Finally, Johan Rodin will wrap up the session with Bring Your Engineering Course Alive with SystemModeler. And of course, you will have time during these to have your questions to us, and we will try to answer them as we go along. So with that, I'll thank you for listening, and we'll be happy to answer some questions before we start next session. Thank you very much.